Colligative properties. So this is, for us, maybe a rhetorical question. Why do you add salt to an ice cream maker? We made ice cream last week, right? Why did we add the salt? To make it colder. It will lower the temperature at which the water freezes to about minus 10 degrees Celsius. And freezing point depression is one example of a colligative property. There's several of them. These are properties that depend on the number of particles. Doesn't matter what the particle is, it's the number of particles that affects the freezing point depression. For electrolytes, what do electrolytes do when we put them in a solution? They separate into ions and they can conduct electricity. That's why we call them electrolytes. So the colligative properties of electrolytes are going to be a little different because 1 mole of an electrolyte will form more than 1 mole of particles when dissolved. So sodium chloride, if you dissolve 1 mole, you're going to get 2 moles of particles. 1 mole of sodium and 1 mole of chloride ions. Another colligative property is vapor pressure lowering. The vapor pressure of a solution containing a non-electrolyte is lower than the vapor pressure of the pure solvent. If we look at the picture, we've talked about the dynamic equilibrium involved in vapor pressure and evaporation and condensation. So we have molecules evaporating into the gas state, we have gas molecules condensing into the liquid state. Dynamic equilibrium, these are happening at equal rates. Well, what happens when we put a solute in here? A solute is going to take up some of the spaces at the surface of the liquid. And so that's going to reduce the rate of evaporation because there's obstruction here. And so the condensation will continue, the evaporation is smaller, and these will adjust because as this concentration in the gas phase becomes lower and lower, the rate of condensation becomes smaller, and eventually you'll get a new equilibrium. But the new equilibrium will have fewer molecules in the gas state. The number of molecules in the gas state is related to the pressure of the gas, which is what we call the vapor pressure. It's the partial pressure of the gas in that space above the liquid. Any questions? So it's a little bit like, we talked about playing Red Rover as an analogy for the molecules escaping. So what if you were playing Red Rover in a forest and there were a bunch of trees in the way? That would obstruct people breaking through because there's trees in the way, right? And so they can't get through. There's a more fundamental explanation that has to do with entropy, that tendency towards mixing. So if we look at this situation, here we have pure solvent in one beaker and a concentrated solution using the same solvent, but now there's a lot of solute in it, in another beaker, and we put them under this cake cover so that the solvent can evaporate, but it can't leave the area. What will eventually happen is that the level of pure solvent in this beaker will drop and the level of solution will increase. And that almost seems magical or something, doesn't it? That just shouldn't happen. How does liquid get from this beaker to that beaker? Nobody's pouring it. There's no straws or trapdoors or anything. Well, what's going on? There's evaporation. There's evaporation from both of these beakers. Those particles get into the gas state, they bounce around, and eventually they're going to crash down. In this solution, because there's a solute, there's going to be a slower rate of evaporation than in this one. But the rates of condensation will be equal. And so we'll have a net movement of particles into this beaker. So we know that in the same beaker, a pure solvent and a concentrated solution are going to spontaneously mix and form a less concentrated solution. But it's also going to happen if you have separate beakers inside of a sealed container. And it's this spread of energy, it's actually driven by entropy. This solution will become less concentrated. Any questions? It's kind of a weird thing. Well, of course, we like to quantify everything. Raoult's law quantifies vapor pressure lowering. So we've got P solution equals chi solvent, P solvent. So P solution is the vapor pressure of the solution. Chi solvent is the mole fraction of the solvent. Not the solute, the mole fraction of the solvent. Is that mole fraction going, what could we generalize about it? A fraction can't be higher than 1, right? But do you think that mole fraction of solvent is going to be greater than 0.5 or less than 0.5? Probably greater, right? Because the solvent is usually present in greater amount. Now, it's going to depend a little bit on the molar masses, relative sizes, stuff like that. But generally, that the mole fraction of solvent will be larger than 0.5. That guy, I can't remember how to say what that little gray circle is. It just slipped my mind. A lot of things have been slipping out lately. That is the vapor pressure of the pure solvent. And it has to be at the same temperature because vapor pressure is temperature dependent. So we can look up the vapor pressure of the pure solvent. And then if we know the mole fraction, we can calculate the partial pressure, the vapor pressure of that solution. So chi solvent can't be greater than 1. And so P solution, the vapor pressure of the solution, necessarily has to be smaller than the vapor pressure of the pure solvent. So it's directly proportional to the amount of solvent in the solution. If we look at the change in vapor pressure, oh yeah, I was looking at these and I couldn't see the difference. Like, why they're just the same? No, they're not. This is chi solute times the vapor pressure of the pure solvent. So that gives you the change in vapor pressure. This gives us the actual vapor pressure of the solvent in the solution. We could derive that, but I don't think we're that interested in it. Okay, calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. So calculate the vapor pressure. Well, we need the equation for vapor pressure of a solution, right? So the vapor pressure of the solution is going to equal what? Chi something, chi solvent, times the normal vapor pressure of the solvent. Yes? Okay. A little distant and subdued today. It's a little disturbing. So this is the mole fraction of the solvent. The mole fraction of the solvent. We learned about mole fractions on Tuesday. That's going to be the moles of solvent. We don't need ofs. Divided by moles solvent plus moles solute. Remember that? It's kind of a messy formula. Did they give us everything we need to be able to calculate that? Yeah, they did. They didn't make it super easy, but we can do it. So we need moles of solvent. What's the solvent? Water. So we'll take the mass of the water, which they gave us, 285.2 grams. And we're using the molar mass of water, 18.02 grams. Cancel out. Yep, I knew I forgot something. Uh, 285.2 divided by 18.02. I want to keep track of my significant figures, but I don't want to round yet. 15.82. I should have 4 sig figs, so I'm going to throw in a couple extras, 6.9 moles. That's the solvent. So that goes on the top. I don't need parentheses. 15.82. I don't know what's wrong with my head. I seriously do not. That's not a 2. It's a 6. 6s look like 2s, but no, they don't. 8269 moles. And that's also going to show up on the bottom as part of the moles of solution, which is the solute plus the solvent. And then we need moles of the solute, right? The reason they gave you the formula here is so that you could calculate the molar mass. 76.11, thank you. So we just add up all the C's and H's and O's. We have 55.3 divided by 76.11, 0.72658. That has 3 sig figs because of this guy over here. Moles. I have to write a little smaller, 0.72658 moles. When we add these two numbers in the denominator, how many significant figures is that number going to have? 4. So, good grief train. The engineers have been very creative with their whistling today. Have you noticed that? Very creative. It's not appreciated. I want to hear them, play Mary Had a Little Lamb or something. When we add those two numbers together, we get 16.55348. And when we're adding numbers, remember, we're looking for the largest uncertainty, right? This number has uncertainty in the hundredths place. That would be this 5. This one has uncertainty in the thousandths place, which would be over here. So we can only keep one uncertain digit, and so we would say this number has 4 significant figures. That one has 4, this one has 4, so our mole fraction has 4 significant figures. Mole fraction is 0.9561. So chi equals 0.9561. But then I'm going to throw a couple extras in for good measure. If you end up with a mole fraction that's greater than 1, you have a problem, and you need to do something about it. So the vapor pressure will be the mole fraction, 0.956107. That doesn't have a unit, times the vapor pressure of the pure solvent, which is 23.8 torr. So I'm going to take that number still in my calculator and multiply by 23.8 torr, and I'm going to get 22.8. Pardon me? You do not need to convert the torr to atmospheres. That's a good question. If you want the partial pressure of, if you want the vapor pressure of the solution in atmospheres, then you'd have to convert. But it's not specific to any one pressure unit. Any questions?
The temperatures are going to be the same always?
The temperatures need to be the same. And they're telling them to you so that you understand that you're just comparing at the same temperature. So, any other questions? In order to do a problem like this on an exam, they have to give you a lot of information. Because you would not be expected to know what the vapor pressure of water is at 25 degrees Celsius. The only vapor pressure that you would be expected to know is that at the boiling point of a liquid, its vapor pressure is 1 atmosphere, or 760 torr. So at 100 degrees Celsius, the vapor pressure of water is 760 torr. But the rest of it, you would just look up in a table, or here they'll just give it to you. What if we have a volatile? Oh, there's a typo. Vapor pressure of solutions containing a volatile non-electrolyte solution. Not cool. Okay, that's supposed to be solute. Oh, I can do better than that. No. I'll do it this way. Oh, look, it just disappeared. There we go. Vapor pressure of solutions containing a volatile solute. It's a non-electrolyte. If the solute is volatile, it evaporates also, and it's going to contribute to the vapor pressure. We've talked about ideal gases. There are such things as ideal solutions. An ideal solution obeys Raoult's law at all concentrations of both solvent and solute. The total pressure above an ideal solution is the sum of the partial pressures of the components. So if your solute is volatile, let's say B is the solute, it's going to contribute to the total vapor pressure of the solution. Non-ideal solutions do not follow the rules. They don't follow Raoult's law. And that's because these have solute-solvent interactions that are either stronger or weaker than the solvent-solvent interactions. And so those intermolecular forces between the solvent and the solute particles mess things up. So here are some graphs. What do these mean? Let's look at this one. This is an ideal solution. And so we're graphing the partial pressure of component A in red and the partial pressure of component B in blue. And this is the mole fraction of A. So 0 to 1. At 0, there is no A in the solution. It's all B. And so the vapor pressure of B is up here. The vapor pressure of the solution is equal to the vapor pressure of B. At the other end, we have all A and no B, and so the vapor pressure of the solution is the same as the vapor pressure of A. In between, for an ideal solution, you have a straight line, because this is the sum of the partial pressures of B and A. And these vary linearly with concentration, and so this ends up being a line as well. If we have strong solute-solvent interactions, the solute and the solvent are very attracted to each other. What's that going to do to the vapor pressure? Is it going to make things evaporate faster or evaporate slower? Slower. Because what happens is you think about the solvent molecules, and they have to have a certain amount of energy to break loose, right? And the solute molecules, same situation. Well, the solute molecules, if they're attracted to the solvent molecules, that in essence is making the intermolecular forces stronger. Stronger intermolecular forces means a lower vapor pressure. And so what we see here is the points at the end are still the same, because here we have all A and here we have all B, and there's nothing for them to interact with. But as we increase the amount of A, it will begin to interact with B, and we see the actual vapor pressure of B dip down below the ideal. And so the vapor pressure of the solution, being the sum of these, dips significantly below the ideal. If we have very weak solute-solvent interactions, meaning the solute and the solvent don't like each other all that much, that's going to drive them to evaporate a little faster. It's essentially lowering the strength of the intermolecular forces. So both of these curves bulge up, the vapor pressure is higher, and we see that the vapor pressure of the solution increases as well. So we have a solution of benzene and toluene that is 25% benzene by mass. The vapor pressure of pure benzene and pure toluene at 25 degrees are 94.2 torr and 28.4 torr, respectively. Assuming ideal behavior, calculate the following. The vapor pressure of each of the solution components in the mixture. Well, that's the same equation we used before. The vapor pressure of this, the part that we're interested in, let's call it A. I wasn't real careful when I wrote the equation in the previous example. Is going to be the mole fraction of A times the standard or normal vapor pressure of A. So what we need are the mole fractions of these two components. Can we figure that out? Yeah. Is it going to be super simple? No. We're going to have to think about it. What does 25% benzene by mass mean? 25 grams per 100 grams of solution, right? I'm going to actually get rid of this word example because I need some space. So 25.0, so 25 grams benzene, I'm just going to call him B. we'll call them B and T, benzene and toluene, per 100 grams of solution. Well, in 100 grams of solution, 25 grams is B, right? How many grams are T then? The rest of it, 75. Everybody okay with that? So we need mole fractions. We've got grams. We need to change these numbers into moles. So we're going to need molar masses. So somebody find the molar mass of benzene for me, and somebody else find the molar mass of toluene. So I'm going to take 25 grams of benzene and figure out how many moles that is. Anybody have the molar mass yet? 73.074. Thank you. So 25 divided by 73.0. Oh, 78? Oh. Okay. And nobody else did it, so, or if they did, 78.114?
Yeah.
Okay, there we go. 78.114. 25 divided by 78.114. So that's 0.01280 moles. That's only one extra sig fig, but I think it'll be okay here. Now, what am I doing? I am being just so dumb. It doesn't go in there. I'd like to say I was, doing this to see if you're awake, but apparently I'm not awake either. So. Maybe I should offer extra credit for anybody who can catch my mistakes. Would that wake you up? Then I have to keep track of it, though. Moles of B benzene. So then I want to take, I hope somebody's got the molar mass of toluene.
93.08.
93.08, thank you. So I'm going to take 75 grams and divide by 93.08 and come up with the moles of toluene. 0.80576 moles of T. So the mole fraction of benzene then is going to equal the moles of benzene divided by the total number of moles in the solution. So it's 0.012802 divided by that number plus the moles of toluene, 0.80576.
Okay.
Yes?
For the moles, it's 25 grams over 78 grams.
Mm-hmm.
That you have 0.32 for that.
Oh, did I do that wrong? 25 divided by 78.115. Yes. Okay. Thank you. Thankfully, I have a really good eraser. Doesn't it work beautifully? It's awesome. I love a good eraser. So we'll try that again. 32005. That looks better. So that one has 3 sig figs, and this other one has 3. When we add the denominator together, it's going to bump up to 1 point something, but it's still going to have uncertainty in the third decimal place. That'll give us a total of 4 significant figures, but we only have 3 on the top. So it's going to end up being 3 anyway. 0.32005 plus 0.80576 equals invert times 0.32005 equals, so that comes out to be 0.2843. That's the mole fraction. That's a 4, not a 9. It looks like a 9. That's the mole fraction of benzene. So to find the vapor pressure of benzene, then we take the mole fraction times the vapor pressure of pure benzene. So the pressure of benzene, I'm still calling him B, will be 0.2893. No, let's see, it's a 4. 2843. Can't read my own writing. Times pure benzene, 94.2. .78 torr. We would round that off, but I think we're going to end up needing that number. So we'd round that to 26.8 for a final answer there. What is the vapor pressure of the toluene? Well, we need the mole fraction of toluene. We only have 2 components. One of them has a mole fraction of 0.2843. The other one has to make up the difference between that and 1. The mole fractions have to add up to 1. So the mole fraction for toluene equals 1 minus 0.2843. Oh, I shouldn't write it there. 0.7 what?
7157.
7157. Thank you. Equals. So then the pressure, partial pressure of toluene is the mole fraction of toluene times its pure vapor pressure, 28.4 torr. Come on. 28.4 times 0.7157. 20.33. Torr. So answering that, we would call it 20.3 torr. We would call this 26.8 if that was our final answer. Any questions? The hard part about a problem like this is the conceptual, what am I doing, where am I going? You start calculating things, you get lost, you forgot what you were trying to do, that sort of thing. It's just, adding, subtracting, multiplying, and dividing. What's the total pressure above the solution? We're assuming ideal behavior. It's going to be the sum of the two vapor pressures. So the total pressure is going to equal the 26.78 torr plus the 20.33 torr. Uh, 47.1 torr is the total pressure. The composition of the vapor in mass percent. Is it going to be the same as the solution? Well, the question down there suggests that it's not, right? It says, why is the composition of the vapor different from the composition of the solution? Can you think of a reason why it would be different? What's different about these two chemicals, these two compounds? Their masses are different. What else is different? Are their vapor pressures different? Yeah. So one is more volatile than the other. Which one's more volatile, benzene or toluene? Which one's going to evaporate more easily? Benzene. Benzene has a higher vapor pressure. So in the vapor, there's going to be a higher percentage of benzene compared to the solution, because the benzene evaporates faster. More of it evaporates than the toluene. So how do we go about calculating this? That's a thinker, huh? Everybody stumped? Well, mass percent, what's mass percent? It's the grams of one of them divided by the grams of the mixture, right? Times 100. That's what mass percent means. So we need to find masses of gases. And we don't have a quantity. We need to make up a quantity. We need to, what's the volume of this gas? We don't know. What would be a real convenient volume to use? A liter? Or 22.4 liters. .4 is a magic number at what temperature? At STP, which is how many Celsius? 0. Are we at 0 Celsius? No. What do we know about the relationship of the pressure of a gas and the number of moles of a gas? If we increase the number of moles of gas, does the pressure increase or decrease? You put more gas in and the pressure goes down. You put more gas in, the pressure goes up, right? The pressure of the gas is directly proportional to the number of moles of the gas. If we could find moles of these, we could find masses, right? So we have these pressures and a total pressure. And we know that the pressure is proportional to the number of moles. There's a number of ways we could do this. My brain right now is just like spinning, going back and forth between different ways. It's just not real effective. So we did this last little problem, which it took up a board and a half. So we didn't have room to put it all on the slide. So I'm just going to give you the answers, you YouTube people. I like you, so don't feel offended that I'm calling you YouTube people. The percent benzene comes out to be 52.5%. The percent toluene is the rest of 100, so 47.5%. And you may be asking, how did we find that? We used the ideal gas law. We said, we'll just pretend we have 1 liter. So we rearranged the ideal gas law, N equals PV over RT. We plugged in 1 liter, the ideal gas constant, and 25 degrees Celsius, which is 298 K. We converted the pressure to atmospheres, we calculated the masses, and then we used the percent mass equation and came up with these percentages. Anybody here have any questions? Wasn't that fun? That was thinking. That was thinking about something, and that's what we expect of 1A students, is that you can think about stuff. Yeah, that's the one we just did. Okay. Freezing point depression and boiling point elevation. We talked a little bit about freezing point depression at the very beginning, and then we went into the vapor pressure. Here's our phase diagram. There's my arrow. So here's our phase diagram. We have increasing pressure on the left, on the vertical axis, and we have temperature on the x-axis. My pointer has a mind of its own. So if we take this liquid and we add a solute to it, that lowers the vapor pressure. Let's think about it up here. So here's the pure solvent. If the vapor pressure is lower, that means that my brain is dead. Okay, major brain fart. I was looking at the wrong axis. So here, when we add a solute, we get to the red line, the vapor pressure is lower. That vapor pressure will be lower at all temperatures. So this red curve here shows the lowered vapor pressure. Well, that causes this to intersect this line between the solid and the liquid and the gas. The triple point then moves down. I can't seem to be able to point at the triple point. There. There we go. There's the triple point. The triple point has moved down. The freezing point, as we go across at 1 atmosphere, the freezing point of the pure solvent is here. Because of the vapor pressure lowering, the solution now will freeze at a lower temperature. I'm sorry, Yeah, well, it'll freeze, it'll also melt at a lower temperature. I'm just so glad they can't see me. Okay. Oh, we need to go back to that crazy slide. So what happens here is the melting point goes down, the boiling point goes up. I used to have a hard time remembering which was which. This is another instance where you have two things, one's going up, one's going down. How do you remember? Adding a solute causes the solvent to be a liquid over a wider range of temperatures. So it pushes the freezing point and boiling point away from each other. Freezing point goes down, boiling point goes up. Freezing point depression can be described by this equation. The change in the freezing point, and that's generally reported as a positive number, even though we know that it's going down, but we report it as a positive number. That's equal to the molality of the solution. Remember, molality is moles of solute per kilogram of solvent times a constant. That constant is going to be different for each solvent. So a relatively simple equation. Here's a table from your textbook showing the freezing point and boiling point constants for several different common solvents. So for water, the freezing point depression is 1.86. The boiling point elevation constant is 0.512. And these units are a little funky. Degrees Celsius per molal. And that's so the units work out. We also need to know what the normal freezing point and normal boiling points are, because the equation gives us the change. It doesn't give us the actual new freezing point. It gives us the change. Calculate the freezing point of a 2.6 molal aqueous sucrose solution. Well, we're going to need some information. Here's water. It was aqueous. We know that water has a normal freezing point of 0. This is what we need. Kf is 1.86. Freezing point depression for water equals 1.86 degrees Celsius per molal, not meter. The change in the freezing point is equal to the molality times the freezing point depression constant. So here, maybe to make up for that last horrendous problem, they just fed us numbers, right? 2.6 molal times 1.86 degrees Celsius per molal. That shouldn't be too hard to deal with. 2.6 times 1.86. So the freezing point depression is 4.8 degrees Celsius. The molals cancel out. What is the freezing point then? This is the change in freezing point. Does the freezing point go up or down? It goes down. So the new freezing point is going to be minus 4.8 degrees Celsius, because it's the regular freezing point is 0 and we subtract the change. So we get minus 4.8. Everybody okay with that? The freezing point depression, the freezing point goes down. So you take whatever the normal freezing point is and you subtract this delta TF. For boiling point, you add it to the boiling point, and freezing, you subtract it. So boiling point elevation, same equation with B's instead of F's. Change in boiling point, molality again, boiling point elevation constant. We saw those in that table a couple slides back. So if you have a car or have had any reasonable experience with a car, you know that a car needs fluid in the radiator, right? In a pinch, you might be able to get by with water, But really what you want is antifreeze. And antifreeze suggests that this keeps it from freezing, right? It's against freezing. Now that doesn't matter so much around here, but where I grew up in Minnesota, it's pretty significant. You don't want your radiator freezing solid. Water expands when it freezes and has a tendency to break your radiator. Leaks real bad. Around here, though, it gets really hot in the summer, and the radiator is cooling off your engine, that coolant that flows through there, and so you don't want the water boiling, because then it generates a lot of pressure, and you've got a pressure valve on your radiator cap that will let the extra pressure out. That's why you sometimes see a car with steam shooting out of it. And if that doesn't work well, then the pressure will break your radiator, and that's when you get the huge clouds of steam coming out. That's not good either. So antifreeze is really neat because it lowers the freezing point and it raises the boiling point. And both of these are really good things for your car. Calculate the boiling point of a 3.6 molal aqueous sucrose solution. So we need that elevation constant, 0.512. That's for water. So Kb equals 0.512 degrees Celsius per molal. And just the units on that constant could help you calculate the boiling point elevation. Boiling point elevation is the molality times that constant. Here the molality is 3.60 times 0.512 degrees Celsius per molal. This is such a dumb word, but whatever. 1.84. So what is the boiling point then? 101.84. We need to take the normal boiling point and add the change. Because if you stop and think about it with your thinking cap on, you realize, wait, it's going to boil at 1.84 degrees? That's not right. It'll boil in your refrigerator. It's 101.84 degrees Celsius. Any questions? Another colligative property, osmotic pressure. Well, this is one long section. We're on 53 minutes here in the same video. Oh well, osmosis. Where have you heard the word osmosis outside of a classroom? Well, yeah, you hear it in biology, but you hear it in TV commercials for water purification systems. Reverse osmosis water purification, right? Osmosis is the flow of solvent from a solution of lower concentration to higher solute concentration. And this is the process by which seawater causes dehydration, and it has to do with the spreading of matter, entropy. I like to think of it as, we're just trying to level everything, and it's like this is low concentration, this is high concentration, we all need to be the same, and so we're going to move solvent from the low concentration to the high concentration, because that's going to dilute it. It's always trying to get everything level. So semi-permeable membrane, semi-permeable, meaning it's partially permeable. Stuff can get through it. Some stuff can get through it. It allows some substances to pass through and not others. Biological cells contain semi-permeable membranes. They have them on the outside, and they also have them on the inside, dividing all those little different parts of the cells that they made you color with colored pencils in biology, right? So here's an illustration of an osmosis cell. So here we have this glass tube, and down here in the middle, instead of it being just open, there's a semi-permeable membrane here. And this allows water molecules to go back and forth, but the solute particles are too large and they can't get through. So we have pure water on the right side and we have a solution on the left side. And the water can go back and forth. So the water is going to go mostly towards the more concentrated solution. It's trying to level things out. It's like they've got high concentration. We've got low concentration. That's not good. Let's send some of our people over there, right? And level things out. Another way to think of it, you have water molecules going back and forth here. Over on this side, you've got solute particles in the way. And so the rate of water molecules going from the left side, the more concentrated, to the less concentrated side is going to be less than those going the other way. Going from less concentrated to more, there's nothing in the way. And so we're going to have a net flow of water to the more concentrated side. It's not going to go on forever, though, because as the level of water in this side rises, we get a pressure difference. When we talked about gases, we said, a manometer can be used to measure the difference in pressure between two gases. And you separate them by a tube containing a liquid, and the height of this liquid represents a pressure. So it will continue to go until it gets to a certain amount of pressure. And that's called the osmotic pressure of the solution. And the amount of that is going to depend on the concentration of this solution. Another way to think of it is that this is the amount of pressure that you would have to apply to this side of the tube to keep the osmosis from happening.
So you said on concentration, it's going to depend on the concentration.
It'll depend on the concentration of the solute.
What about viscosity?
Viscosity, well, if we're talking about an aqueous solution, the viscosity on this side is always going to be the same. The viscosity on that side would depend on the amount of solute in it. Like if you think of like corn syrup, what's the solvent in corn syrup? Well, there's a lot of sugar in it, but what's the liquid in corn syrup? It's water. There's just a lot of sugar in it, right? And so it is more viscous, but it's more viscous because it has more solute in it. And so the same thing would be true.
So osmosis follows the pressure gradient?
Well, osmosis happens to equalize the concentrations. And that that results in a cell like this in a difference in pressure. So what do you think reverse osmosis is? It's the opposite. The flow of solvent molecules from a more concentrated to a less concentrated. How could you make it do that? It doesn't want to do that, does it? Pressure. If we put a lot of pressure on this side, then we can force the water into the other side. The solute particles are too small to go through the membrane. And so you can purify your water in that way. And it sounds all fancy, reverse osmosis. So osmotic pressure, you say it's the pressure required to stop the osmotic flow. And so that's a capital Pi. This looks like a shouting equation, right? Capital Pi equals capital M, capital R, capital T. It's yelling at us. M is the molarity. T is the temperature in kelvins, and R is the ideal gas constant. So here, the ideal gas constant is liter atmospheres per mole Kelvin. And we've got a molarity, which is moles per liter. And so it's going to work out to be atmospheres for the osmotic pressure. Let's do an example. Calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. Osmotic pressure equals mRT. So we need the molarity, we need the ideal gas constant, and we need the temperature in kelvins. What's the molarity of the solution? We got to calculate it, don't we? So 1.50 grams of ethylene glycol. That is probably the most common antifreeze. So 2 times 12.01 plus 6 times 1.008 plus 2 times 16, 62.068 grams per mole. Zero 0.024167 moles. Then we need to divide by the volume in liters. So the molarity is going to equal the moles. What's this guy? Moles divided by liters. 50 milliliters is 0.0500 liters. So we get 0.48334 1 molar. Pardon me? Oh, yes, it is. Thank you. And now it's an 8. 0.48. Yeah, I actually just left out. I left out a 3. No, I left out the, I don't know what I did. I just left out the 8. Doesn't really matter, does it? I'll stop talking now. That's just lovely. Moles per liter. Okay. So now we can go to our equation here. 0.48334 moles per liter times the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin, times the temperature in Kelvin. So moles cancel, liters cancel, Kelvin cancels. I get 11.8. 11.8 atmospheres. Is that a high pressure or a low pressure?
High.
That's high. 11 times atmospheric pressure. That's pretty high. Any questions? Oh, thank goodness.